Hello everyone. So I am Cherif from China University. So I present today our work on novel design and multi-objective optimization of autothermal steam transformer to enhance hydrogen conversion and thermal matching. So first I'll start with introduction, mathematical model, optimization approach, results and discussion, and conclusion. So, as you know, the storage of excess renewable energy via conversion into hydrogen is indispensable for the transition to clean energy-based economy. So, methane can afford the highest percentage of hydrogen storage of 25% compared to other materials such as metal hydrates or ammonia. And also, methane is the most significant source of hydrogen with 50% worldwide. However, for the storage application, there is a big deal with the temperature and thermal, for the thermodynamic limitations and the high operating temperature. So there is variance in the thermal energy, and also as it is very strong endothermic reaction, so we can find that the overall efficiency of the power to gas to hydrogen process is about 20%. So this leads us to talk about the heat supply methods for steam methane forming reaction. So the main used method is the external heating for the steam methane forming using the coal-fired box or the furnace to supply heat to the steam methane forming. The second one is the autothermal steam methane forming, which is using the ignited combustion before the leading edge of forming catalyst. And for the third case, it is the catalytic autothermal reactor, where we use a catalyst for the combustion followed directly by a catalyst for reforming. So for these cases, the first one is the most used method for heating. So in our study, we have proposed a model for the steam methane reforming using annular catalyst autothermal reforming. So the catalyst was implemented as a multi-consumption rings in the reactor, alternating between the reforming and the combustion catalysts. And also we have modeled the conventional catalytic autothermal reformer for comparison sake. So the main difference is for the annular catalyst we have used more combustion catalyst because of the length of the reactor, which is 1 meter. And also this leads obviously to more percentage of volume ratio. And also we have used 4 catalyst layers for the combustion, while the rest is the remaining is for the reforming catalyst. So for modeling this reaction, we have implemented a kinetic model that was developed by Nebbali et al. For steam methane forming and Descent et al. For the combustion reaction. The catalysts used for these 2 reactions are the nickel and platinum for combustion and reforming respectively, and based on aluminum. So for the mathematical model, the governing equations, which are the continuity, momentum, the energy and species equations were used. And for modeling the catalyst structure, the catalyst force media, we have used the Darcy-Brinkmann-Franchheimer model equations. So for the catalyst, we also assumed it to be in thermal equilibrium with the fluid. For the resolution method, we used the finite volume method for the discretization of the partial differential equations, while for solving the velocity pressure field, we have used the simple algorithm. So we have built a code using Fortran language And we for the CFD model, we have used Python for the genetic algorithm coded. So for the computation, for the resources we have used the 20 CPU in parallel, and we have used the calculation was implemented for around 3-4 days. So for the hypothesis, the main hypothesis were the steady state to the laminar and the compressible flow. So for the boundary conditions, we have used the uniform inlet velocity, temperature, and molar fractions. While for the wall, we are using no slip condition and the adiabatic impermeable wall. For the outlet, we have used the fully developed flow. So for the validation of the model, we have compared the numerical model with the results of a study published by Chung et al. So as you can see, there is good arrangement between the two, between the numerical and the experimental results with a maximum error of about 4%. So for the optimization approach, we have, as you can see here, there is implicit, or the first one is explicit explicit optimization. So instead of, it's very complex, and we have to find the position and the diameter of each catalyst. So instead of this, what we did, we have used an implicit optimization. Sorry for the notations. The second is implicit. So instead of finding the distance of each catalyst, we have predefined 20 segments. So what we will find, what we will seek is finding each position if it's reforming or combustion catalyst. So this can reduce the time of optimization and also reduce the complexity. So, so the objectives of the optimization are the higher yield and also the low temperature on the wall. And also for the lateral objective, we have implemented it to avoid using over combustion catalyst. So we have used the wall temperature as a reference, and also for the mechanical stability, and also for to use lower cost wall materials. We have sought lower temperature on the wall. And so for the genetic algorithm, which involves the generating an initial position, then simulation of 40 population of using CFD for getting the results. Then we evaluate the results using the two objectives. Then we have 3 sections for the selection. We have the direct selection of currents, and then we have the selection. These currents pass by crossover to make new elements, and also the same elements pass by the mutation and the random mutation, and then we generate the new generation. This optimization process. This optimization procedure iterates until getting the optimal solution. So for the results, first we compared between the arbitrary set catalysts, which is the proposed design, and the conventional design. So we can see that there is lower average temperature inside the reactor, and for the conventional one, we can see that we have avoided the high increase at the inlet of the reactor, and the plateau that is found because of the depletion, total depletion of oxygen. And for the second figure, you can see we have a problem in the proposed design, which is the hotspot on the wall. So for the proposed design, we have delayed increase of temperature, However, the hotspot is main problem. For the distribution of temperature, you can see that there is a delayed temperature increase in the second, in the proposed configuration, with also hotspots that follow the deposition of the catalysts. For the yield and conversion, performance, we can see that the performance is higher for the proposed model, for the proposed design, and after 20 centimeters. After 200 centimeters, we can say. So after 200 millimeters, we can see that the increase of the yield and conversion in the proposed design is much better, because at first we have lower temperatures. This follows the temperature profile, because there is very high impact of the thermal behaviors. So for the distribution of methane and hydrogen, the distribution of methane and hydrogen for proposed design, we also see that they follow the same distribution of temperature. So this leads us to the optimization results. So to confirm the convergence of optimization, we have calculated the area of the upper area and the lower area. So the proportion between the two was 21, which indicates very high convergence. And also we have very low difference between the two last better results. So this led to indication of convergence. For the compared to the conventional ATR, we can see that the optimal case in the second, from the first figure, which is the first generation, or to the second one, which is the last generation, we can see that the optimal solution and the last generation moves towards lower temperature and towards higher yield. However, there is more improvement in terms of yield compared to temperature, because we have set a higher weight for the yield compared to the thermal behavior, which is 90% for the yield, while it is 10% for the temperature. So for the results, we can see that the optimal case, which is the third one. So for the first figure, we can see that the temperature, for the average temperature inside the reactor, it was decreasing by about 100 degrees compared to the design. While for the wall temperature, we can see that we avoided the hotspot that was present in the design case, and we have also avoided the abrupt increase in temperature and abrupt decrease. And also we can see for the distribution, there is still problem of the hotspots for the catalyst zone, which is in the 5 catalysts. So for this case, for the optimal case, we have gotten 5 catalyst layers for the optimal case. So this, for the summary of the results, so we can see that the maximum temperature was decreased significantly from 1,400 degrees Celsius to about 800 for the maximum wall temperature, which is very significant in terms of the materials choice, and also for decrease for avoiding cracking and having better mechanical stability for the reactor. And for the proposed design, higher conversion of methane and hydrogen yield of 27% and 46% respectively. And also we can see that for the optimal arrangement, it led to 39% lower maximum temperature. So as a conclusion, we have proposed a new design and also a multi-objective optimization analysis for the distribution of conducted design and the affair that is implemented on nickel and platinum catalysts. And also for the design case, a notable enhancement for methane conversion of 27% was observed compared to the conventional case, as well as a decrease of 24% in the highest average temperature and a slight decrease in the maximum wall temperature was achieved. Also, some hotspots were still observed at the wall in the design case. So, for avoiding this, we have implemented optimization. So, the optimal case was sought to limit this hotspot and along with attaining high hydrogen yield. So, this latter was not significantly improved compared to the design case. However, the thermal behavior was strongly enhanced, and the optimal arrangement smoothens the wall temperature profile with 39% lower maximum volume. So this work was published in the Applied Thermal Engineering, so under the title Novel Design and Multi-Objective Optimization of Autothermal Steam Thermoformer to enhance hydrogen production and thermal motion. So the collaborators of this work are Jusong Lee, Racid Nebbali, and Professor Cherif. So also we have implemented this idea in another paper, but focusing on the membrane steam methane reformer. So we have done the same optimization strategy, but for membrane and catalyst alternating, and we have good results for this case too. So it was the design and multi-objective optimization of membrane steam methane reformer, a computational fluid dynamic analysis. So thank you so much for this.
Thank you for your nice presentation. And again, Jusong.
Hello. Thanks for your talk. As I know that in this SMR, the radiation is very important part of the model. So I don't see the radiation in your governing equation. So did you estimate that how much percentage the radiation could affect to your results?
Actually, for this, the internal radiation between the two catalysts was not considered because, as you can see, the temperature profile inside the reactor, there is for the radiation, there is no big difference in temperature, so the radiation can be ignored for this.
I mean just the hotspot space, and also the other question is that usually for this the reactor to eliminate the hotspot, usually they mix the catalyst with some material with the high thermal conductivity so then you compare your optimized model with some scenario that
yes, for there is cases where they use high conductive materials, but the point of the work is finding a design that reduces that limits the hotspot, but at the same time avoiding using high cost materials or this is
okay, thank you.
Okay, last one more question.
Thank you very much, Dr. Ali. Thank you. I have just two questions. The first one is, what dimension do you use for the reactor? Is it 1D, 2D, 3D? And the Fortran safety code, was it running synchronously with the GA optimization algorithm, or was it after the CFD results or activities that you decided to optimize. So I want to thank you.
So for the model, it was 2D, and for the optimization, we have synchronized there is like a procedure. First we set a random generation. Then for each element we conduct the calculation. It is calculated in parallel, so because it takes some time. Then this is how it is. The CFD model and Python code was integrated.
Okay, thank you again. Please give a big pleasure to